Hi, and welcome to this informative video on the Wood Shear Wall module in Structural Engineering Library. The purpose of the Wood Shear Wall module is to evaluate the unit shear in sheathing of a lumber framed wall, to evaluate the chord stresses, tension and compression stresses at the jambs and chords of the wall, and if desired, to design a continuous footing underneath a wood-framed shear wall. Now there are some important details to be aware of regarding this module and its use and its limitations, and those are all presented in the corresponding section of the user's manual, so don't forget to take a look at those before you get too far into the module. But for now, let's just highlight its use. I'll add a new wood shear wall module calculation to this project file by clicking on Calculations and then using Add. And here in the wall category, I'll click on Wood Shear Wall. Now that we're actually in the Wood Shear Wall module, we can see that, familiar to most of the structural engineering library, we have a screen layout that puts the input portion at the top half of the screen with a variety of tabs, and then we have the output or results panel at the bottom half of the screen, again with a variety of tabs so that we can look at multiple types of output information. Just as a quick overview, notice the tabs that are available. We have a general tab, which is the one that we're looking at now, that collects some information that's general to the overall design. And then as we look down the line through the normal workflow progression, we can see that we'll have a tab that will collect information on the sheathing that we want to use for this particular shear wall, information about the chords of the wall, information to define any openings that may be present, an option to define a continuous footing underneath the full length of the wall if desired, a tab that will allow us to define the loads that act on the wall, and finally a tab that allows us to define our load combinations for the different types of analyses and design that will take place within the module. So with that basic overview, let's now start to look in detail at the different tabs that we have available to us, starting with the Input tab. Specifically, we'll begin with the General tab. The Description field allows us to enter some sort of frame of reference of our project. So maybe this is the wall on line 1 between A and B. The total wall length input is just that. It collects the full length of the wall that you're going to define as a single shear wall, potentially including openings, but not necessarily having any openings at all. So let's just assume that we're going to define a wall that is 25 feet long for this example. In the story heights category, what we do is we define the heights of all of the potential stories that exist within this wall. So let's just assume that perhaps this is a 3-story tall wall where we have story heights starting out at the lowest story, which is going to be 12. Then what we do is we come to this input field and we say perhaps that the second story will have a height of 11 feet. And when we press the Tab key to enter this value, notice that it automatically pops open the next input field for the next story above. And so let's just assume that that story height is 10 feet. So we have 12, 11, and 10. When I click to enter this information, notice that it does populate or offer another input field here. That's just available in case there happened to be a 4th story, but in our model there is no 4th story, and so we just leave that 0. Don't worry about deleting that or removing it, just leave it set to 0, and that tells the module that it has a 3-story model to deal with in this case. Notice that the total accumulated height is reported here for our convenience, so we have base to top dimension of 33 feet in this case. The seismic design category is provided here in a drop-down list box form, and the purpose of the setting here is to check to make sure that the sheathing that we eventually choose on the next tab is actually allowed, because the special design provisions for wind and seismic in the 2008 version of the special design provisions for wind and seismic do provide some limitations on the types of sheathings that can be used in different seismic design categories. So we will collect that for you and then flag any conditions that are violated downstream. Moving to the upper right hand corner, we have a design method toggle where we can choose to either design according to ASD or LRFD. I would point out that design method is applicable to the design of the sheathing and the fastening, and it's applicable to the design of the cords, the wood cords within the wall. If you choose to design a footing, that will obviously use normal LRFD or ultimate load design for concrete. So this does not affect the design method of a concrete footing. The last thing that we have to enter here on the General tab is the framing and cord material. Notice that there's an icon over here to the right which opens the wood reference design values database that's typical throughout the structural engineering library. So what we can do here is come into the appropriate size class. We can move down through and perhaps we choose balsam fir number 1 for interest's sake, and then click select, and notice that that populates all of these fields with the appropriate information for the material properties, including the specific gravity, which will come in important downstream when we take a look at one of the adjustments to the unit shears for the sheathing. And all of these are populated automatically for you. Note that this is indicated as the framing and cord materials. So the assumption here is that you will be using this specified material as the framing, the common framing throughout the wall. In other words, all sills, top plates, common studs, as well as jambs and cords will all be of this same material. Next, we'll move over to the Sheathing tab, and here we can see that we have a category that collects information about what's referred to as the main sheathing. In other words, on all shear walls, at least one side has to be sheathed. So we refer to that as the main. And within the main sheathing category, we can choose which construction table we want to draw from the special design provisions for wind and seismic. So that includes tables 4.3a through D of different types of construction. Let's just assume for this example that we want to draw from table 4.3a, and we can come down and choose a wood structural panels of a certain thickness and of a certain minimum fastener penetration and fastener size. So we'll choose wood structural panels of the structural 1 category, 15/32 1 3/8 inch minimum fastener penetration, 8 penny fasteners. As soon as we make that choice, the nominal seismic shear capacities are populated in the small table below for various fastener spacings, and the nominal wind shear capacities are reported. Now, note that these are nominal capacities, so they are not yet factored or adjusted for the various items that need to factor in to the design. They're not at an allowable strength. They're not at an LRFD strength. These are the nominal values, and from there they need to be factored appropriately. But they're here for reference, and these are the values that you would read directly out of the corresponding table in the special design provisions for wind and seismic. So, a handy reference piece of information there. The last thing to note in this table is that there's a category or an option to indicate whether or not the sheathing is blocked. This affects an aspect ratio check that's performed downstream and reported down here as a piece of information for us in the results category. So just make sure that that is toggled appropriately. Actually, there is one more piece of information that occasionally occurs in the lower left-hand corner, and I'll see if I can fish for one of these sheathing options. There's a very specific selection within one of the tables, here we are, that has a footnote that corresponds to it in this particular table, specific only to certain selections within that table. And so if you happen to choose one of those combinations of sheathing and fastener penetration and fastener size, you have the ability to indicate whether or not that particular footnote applies. Just wanted to make sure that I pointed that out, but let's just return to the original sheathing combination that I've chosen so far. Now, to the upper right hand portion of the screen, notice that there's a checkbox beside sheathing on a second side. So if we happen to have a wall that is only sheathed on one side, or if we only want to consider the resistance of the sheathing on one side of the wall, then we can leave this checkbox deselected. However, let's assume that we happen to have a wall that's perhaps an exterior wall, and it's sheathed on one side with wood structural panels, and it's sheathed on the inside with some gypsum board. So we can select the checkbox that says that we do have sheathing on the second side. Now, notice that we also have a convenience checkbox here to say simply the same sheathing as what was defined for the main side, which just adopts here the same thing that was defined here. But for our little example, let's assume that we happen to have something that's gypboard on the inside face. So we'll come to table 4.3c, which defines the options for gypsum board walls. And then let's just choose this particular option here, and for convenience to read the whole description, that is 1/2-inch gypsum with 5-penny cooler nails at a 7-inch edge spacing. Stud maximum spacing is 24 inches. Just for convenience, let's come down to one that's 16-inch spacing. And notice that here there's an option to indicate whether the construction is blocked or unblocked. Since we made over here on the main sheathing that the framing will be blocked, or the sheathing will be blocked, let's just keep that consistent since the blocking will be shared. Okay, so we have that 7-inch edge spacing with the 5-penny cooler nails and a maximum stud spacing of 16 inches, acknowledging that this framing will be blocked. Now what we can see is that the nominal seismic shear capacity is 250 PLF, and the nominal wind shear capacity is also indicated as 250 PLF. So now we have both sides of the sheathing for our particular wall defined. We'll move over to the Chords tab next. The first thing that we do on the Chords tab is we define the member size and about the definition of chords in the Wood Shear Wall module is that we are going to define the size of the individual lumber member that will comprise the chords at all locations within each level, and then the module will determine for us how many of these members we need at each location. So for instance, if we happen to have a wall that is framed with nominal 2x6 framing, what we're going to indicate in these drop down list boxes is that we have 2x6. Or if we happen to be working with larger framing for some reason, then we would indicate that framing size. What we're not going to do is presume that we need two 2x6s and therefore choose the 4x6 option. That is not what we do with this drop down list box, and that this note here that says chords and wall will use multiples of the size selected, and that would be as necessary. So let's just assume that we're going to use 2x6 construction for the full height of this wall. So I'm going to indicate 2x6 for level 1, for level 2, and for level 3. Now, the next thing that we need to do is come over to the size factor input. And I don't happen to remember what the size factor is for the particular species that I've chosen right now, but I'm just, for fun, going to take a guess at 1.15 for a 2x6 of, I think we chose some sort of hemlock. So let's just key in a value here. Notice that the chord is calculated for us, and that's just a convenience thing so that we can see what size member, what area we're dealing with for each of those individual members. Again, just want to underscore that if necessary, the module is going to indicate that we need to double or triple and so on at each location. Let's move to the upper right hand side of the screen here. We have a maximum chord stress ratio that we can enter. This is a convenience tool in case for some reason you want to experiment with some higher than normal stresses. Maybe you're doing something with an existing condition and you need to play some numbers to try to get something to satisfy your threshold for a minimal amount of overstress. This is a way that you can do that, but the intention for normal use, for new construction, for all normal loads and load combinations according to today's building codes and design standards, we would expect that 99% of the time this will be set to a value of 1.0. So we're looking at just meeting allowable chord stress ratios. Now, having said that, I suppose that another way that this could be used is that you could factor this down. You could enter something like a 0.9 or a 0.75 if you wanted to reserve some capacity, say for instance for some potential future expansion or for some contingencies on some loads that can't fully be quantified right now but can only be somewhat anticipated qualitatively. For our purposes, we'll leave this set to a value of 1.0. The last thing that we need to do here on the chords tab is make a decision on how the chord strength will be calculated, and it has to do with the compression strength of the chords. There are two options. The first option is to treat all chords as though they were fully braced about both axes. What this means is to assume that buckling cannot occur. Now, I'll say that this is probably not the typical option that would be selected. Let's think in terms of a physical analogy here. One way that this could potentially be a viable option to select is if you happen to have, say, a U-shaped or a T or an L-shaped framing configuration of shear walls such that your chords were always intersected by walls at, say, 90 degrees to the wall of interest, such that the sheathing within the plane of the shear wall being designed obviously prevents buckling in one direction, and will envision that an shear wall would prevent buckling in the out of plane direction of the wall being designed. And so therefore you might be able to safely say that your chords are completely braced against buckling about either axis. Having said that, for our purposes, I'm going to choose the second option, which says assume that all chords are unbraced out of plane for the full height of the story. This is probably more common, and this is easily envisioned by just picturing a sheathed shear wall in the middle of a building somewhere with no intersecting walls. So what that means is that it's probably reasonable to assume that the sheathing will prohibit any buckling of a chord member within the plane of the wall that's being designed, but there is nothing that's physically restricting that member from buckling out of the plane of the wall. So if we think of 2x6 construction and we assume that we have single chord members at the ends of that shear wall, it can't buckle about the weak axis of the chord member because the sheathing is fastened to it continuously. But there is nothing that prevents that single 2x6 construction from buckling about its strong axis, and so therefore it would be, with this option selected, it would be evaluated in that way, assuming that it can potentially buckle about its strong axis. Next we'll move to the Openings tab, and this brings up a good point about the basic assumptions that are being used in the analysis and design of this module. The module is programmed height shear panels as specified in the special design provisions for wind and seismic. The whole concept of openings is an interesting and challenging topic because it somewhat goes against the concept of individual full height shear panels, except that we were able to find a way to allow you to define openings within your shear wall panels. And then what we did was we basically just declared that the portion of the panel that's, we'll say, violated by an opening is completely without any ability to resist shear. And so what it does, therefore, is it divides one shear panel into two shear panels, one on either side of the penetrated portion, and any contribution to shear resistance from the portion that has the penetration in it is just completely neglected from the perspective of shear resistance for wind and seismic. So let's take a look first at how we can define openings, and then we'll see the result of placing an opening within a wall. Here on the left-hand side of the screen, we have a table that will define all the geometry of our openings, and in order to add an opening, we can use this Add button down below the table. That opens up the Add Opening dialog. It tells us that we're going to be working on an opening that is labeled O1 for opening number 1, and we just collect 4 pieces of information, starting with the distance to the left edge of the wall. So this is from the left edge of the wall to the left edge of our defined opening. Let's just say that we want to place an opening 10 feet over, that we want to, and notice that we have the spin area. Click them an increment at a time if we like to work in that way, or we can just enter the values that we want. Let's say that we have a 4 foot wide opening. The distance to the bottom of the wall, so this is from the bottom edge of the wall measured upward to the bottom edge of the opening. Let's say that we have a door here, so we're going to indicate that it's at 0. The opening comes all the way down to the bottom of the wall. And let's say that the opening height is 7'4", and then we'll click OK, and there we have a door. Now let's say that we wanted to also model a door in the second story. So what we can do is come back to the Add button, and we would say that we want these doors to align. Now there are some important limitations on what can and cannot be done to openings. We'll leave those to the section that's dedicated to that topic in the user's manual, but please do take a look at those. There's quite a bit of intelligence built into the module itself that will flag openings that are not allowed. It'll use some warning text here on the screen, and as we enter some values here to start to define this next door, we may actually see some of that warning text pop up because it's got partial information, so it's going to think that we either have overlapping openings, or we have openings that cross a floor level or that hang partially outside of the wall, and so on and so forth. But just be aware that there are limitations. Generally, your openings want to align vertically, kind of like a load-bearing wall type concept, and please do take a look at that section of the user's manual. Having said that, I do want my doors to align, so I'm going to provide the same distance that was 10 feet. The opening width wants to align, and there we can see evidence of an invalid opening. Something thinks that it's not aligned yet, and that's just because we haven't fully populated the information for this opening yet. So it's checking as we go and giving us real-time feedback on the opening that we're defining. The distance to the bottom of the wall. We have to remember now that we defined our first story as being 12 feet tall. So the distance to the bottom of the wall from the bottom of the opening will be that 12-foot story height. And then let's just say that this door wants to be the same 7'4". Okay, and there we have a door once again. And then let's further assume that at story 3, for whatever reason the layout changes, we don't happen to have a door there, but we have some windows, and those are on either side of the door. So what we can do now is say that we want to add another opening. The distance to the left edge, here let's put this 4 feet over. It'll be a 4-foot wide window. The distance to the bottom of the wall, we have a 12 and an 11 is 23, and then I want it to be up 4 more, so that's 27 feet up, and the opening height will be 4 feet. And I'll say OK, and there we have a window. And then to define the other window, we could do something similar. We can say the distance to the left edge, we're going to do 17 feet over. The opening width is 4. Distance to the bottom was 27, same sill height, and the opening height is still 4 feet. And there we have a valid configuration of openings, a couple of doors that align, and a couple of windows that do not overlap the openings in the stories below them. Now let's take a quick look at some of what goes on here when we create these openings. The assumption here is that we took the single panel that occurred at story 1 and we just broke that into 2 effective panels, panel number 1 and panel number 2 at level 1. This portion that is at the door opening and the portion above the door head is not considered as being functional for resisting shear at all. It's just neglected when it comes to the shear resistance. So we now have 2 panels here that are effective at resisting shear. And we go through the proper math to determine what the story shear is applied at the top of story 1, and then we attribute that shear to the however many panels are effective at resisting that shear in proportion to the length of each of those remaining effective shear panels. Notice also with the dotted lines that we define chords at these locations, because when we split the wall into effective panels, the individual full height shear panel method dictates that we have to have chords at both ends of all panels. So we have a chord always at the overall end of the wall, but now we also have new chords introduced here, and you would want to validate that in your framing plans and your details to make sure that the tension and compression forces and the anchorage and so on for panels 1 at the lower level can be coupled out by the chords that the program is going to design for you at the jambs of the opening. The same thing holds true for all of the other openings up the height of the building. We have multiple chords that are defined. At the 3rd story we have 1 effective panel, 2 effective panels, 3 effective panels, and so on. Just as a quick prelude to what's coming up in the analysis results, I would also point out that one of the important portions of design of the shear walls, wood shear walls, is the aspect ratio, and that aspect ratio has some limitations on it according to the special design provisions for wind and seismic. Those aspect ratios depend upon the framing type, the blocking configuration and so on. So we are checking all of those aspect ratios for you, and where there's a problem, we're flagging that for you to know that something is wrong. Here, as an example, is one of those notes that says somewhere in here I've created a situation, and it's most likely these panels at level 3, these very narrow panels, they're probably too narrow for their height, and so the aspect ratio is so small that it can't be used. It can't be considered effective at resisting shear, and therefore something needs to be changed in this wall. Okay, in order to simplify some of the output that'll come downstream, I'm going to just delete a couple of these openings, because every one of these openings creates multiple chords and multiple entries in output, which just creates a lot to look at, as you know if you're familiar with the design of wood shear walls. So let's simplify this back down to a wall that just has one single opening in it, and that'll just make things a little bit more convenient when we review output in the other portions of the video. Just to finish this off, notice that if you happen to enter your openings in an erratic order, such that opening number 1 maybe was way up at the top of the building and number 2 is down here and so on, nothing to prevent you from doing that, but it may be difficult to interpret the data afterwards. So we do have a renumber button that renumbers things from left to right and from bottom to top. We have a delete button which allows you to select an opening in the list and delete it. You just saw me do that with the window openings and the door at the second floor. And then we have an edit button which just pops open a dialog that allows us to revise the dimensions and location of the selected opening in the list. The last thing I'd point out is that we do have the ability to turn on and turn off display of certain labels and certain items within the graphic here. So we can turn on dimensions, chords, and labels, the labels for the individual shear panels. And if we had gotten to the point of applying loads, we can actually display all of the loads on the panel as well. So that is a thorough look at openings and some of their effects on analysis and design. We'll now move on to the footing tab. On the footing tab, notice that the very first thing that we have is an option to specify a footing, or to just neglect the design of a footing altogether if it's not appropriate for our design. There may be situations where you're anchoring a shear wall to other construction and a footing is completely irrelevant. Let's just assume that we do have a footing in this case, and I would also mention that when you specify that you're going to analyze and design a footing, it also does have some control over certain options that are offered on the Loads tab as well. So just be aware of that. Within the Footing Design tab, we have the ability to specify our allowable soil bearing pressure so that the module can report an okay or no good status on the soil bearing pressure that it determines. We specify the strength of concrete and the yield strength of the rebar that will be used. We provide the rebar cover, and we specify the minimum steel reinforcing percentage. This is based on the overall thickness, so this will be calculating a width times this factor as a minimum possible reinforcing amount that can be used on the footing. The concrete density is collected in units of pounds per cubic foot, and then from there it's geometric information. So we provide a footing width. This is a dimension perpendicular to the elevation view of the wall. And then we provide a footing thickness. Notice that the thickness is collected in units of inches, whereas the footing width is collected in units of feet. And then we specify the projection of the footing. When looking at the elevation view of the wall, how far does the footing project beyond the left chord of the wall in units of feet, and how far does it project to the right beyond the right hand chord of the wall the module already knows the wall length as defined on the General tab, so it sums the overall footing length for us and indicates that for convenience as 20. So fairly simple input information here on the footing tab in order to collect a design for the flexural steel that is required to reinforce the projections of the footing. And I would point out that at this point the footing module is not looking at reinforcing in the transverse direction or perpendicular to the wall, so it's not looking at wide footing widths here and reinforcing for flexure tending to fold the footing up against the wall, but instead it's looking at the flexure in the shear and flexure in the projections beyond the end of the wall. So just keep that in mind, because you'll want to make sure that you don't specify something that's so long and so thin that that assumption is invalid. We're basically looking at long but thin or relatively narrow footings here, where the primary design consideration would be the flexure and the shear in the projections themselves, not such that there's transverse flexure. Let's now move on to the Loads tab. And here we can see that we have a variety of sub-tabs available to us to help us to define all of the different loads that act on the wall. Starting with the wall self-weight category, notice that we have the option to consider the wall weight as a vertical dead load. So we can come in here and say that perhaps our wall weighs about 6.5 pounds per square foot of wall elevation area, and therefore that wall weight would automatically be counted for us if this checkbox is selected. And notice also that we have the ability to consider the wall weight as a seismic load. So we've defined that the wall weighs about 6.5 pounds per square foot. The assumption here is that we can take that weight and multiply it by the seismic response coefficient that we can define right here, and that will automatically be considered as a seismic load. Notice that in the wood shear wall module, openings are considered to be the same weight as the solid portions of the wall. The reason for that is basically as a simplification, because in wood framed construction of normal nominal dimensional lumber, the openings will commonly be filled with either a door of its construction, or a window of some sort of construction, or a louver, or there may be ductwork framing into it and providing some small amount of weight to that location. So as a simplification, and to try to save you a little bit of extra work of having to model any potential other loads, what we've done is we've simply said, in general, wood frame shear wall construction is relatively light enough that we can simplify it and say that the weight that we're assuming for that construction is approximately equal to the weight of whatever is going to replace or fill that opening, whether it's a door, a louver, a window, etc. So that is important to understand and hopefully convenient. Now the other thing I'd point out is that you don't have to use the wall weight as seismic load. Perhaps you've got reason to apply those loads in a different way. You can simply deselect that option and notice that the CS value or the input collection goes away. And likewise, maybe you've already made an allowance for the wall self-weight in your applied loads that you're going to use these other tabs. You don't have to have the program automatically consider the self-weight of the wall framing. You can just turn that off, and even that input goes away, just to neaten things up a little bit for you. The next categories here are both dependent upon the choice to design a footing. So if we had indicated on the footing tab that we did not want to design a footing, then we wouldn't see an input for soil over the footing, and we wouldn't see added overburden load over the footing either. But since we did select the option to design a footing, then here on the General tab of the Loads tab, we have the option to specify how thick the footing is over the top, how thick the soil is over the top of the footing, and what the density of that soil should be, so that the program can automatically consider the load due to the soil. And then we have the ability to specify further superimpose of all of the different typical load case categories. So we can specify those superimposed loads on the footing in units of PSF, and those would not affect the design of the shear wall, but they would be considered in the design of the footing. And then again, if we take a look at the right hand side of the screen, we have the graphic of the wall, and we have all of the options to turn on and turn off selected items. So we can take a look at individual things and turn on loads for the entire wall, or view only those loads that are specific to the selected tab. That'll make a little bit more sense when I start to move through these other tabs, such as the vertical point tab. And now we can see a note up here that says that the graphic is displaying vertical point loads only. That's going to be made more meaningful if I actually add a point. I can say that I have some sort of load at a distance of perhaps 4 feet over, and we have 33 feet to the top of our wall, and maybe it's a 1 kip point load of dead load magnitude. Positive magnitudes act in a downward direction, so I'll enter that as a positive 1 dead load, and then OK. And there we can see that we have a 1 kip dead load. If I wanted to come to the uniform, the vertical uniform tab, I could add something that starts at the left end of the wall and goes all the way to 25 feet, the full length of my wall. It's located at the very top. It's 33 feet, and perhaps it's a snow load on the order of 500 pounds per foot. Okay. And now I can see snow load 500 pounds per foot. Now I can come down to this all loads checkbox, and I'm supposed to see all of the information for the different loading types. So there we can see, had to just refresh the screen in order to get that view, but we have both the dead load, that's a point load added from another tab, as well as the vertical uniform load from snow added on the currently selected tab. So that is the function of this checkbox, and we can see that we just have a refresh item there that needs to be clicked from one tab to the next to get that to refresh. Moving on, we have a tab called lateral point, which allows us to specify laterally directed loads. So perhaps we have 12 and 11 is 23, something that acts right here at story 2. And let's put this on as a 2 kip wind load. Okay, is a laterally directed concentrated load or point load. And then finally I have the ability to define lateral uniform loads. So I can say that it starts at 0 above the base and goes all the way to 33 feet, the full height. And maybe this is a 800 pound per foot seismic load acting on this wall. And then I can say OK, and there is my seismic load of 800 pounds acting from elevation 0 to elevation 33. Now within each of these tabs we have the familiar add, edit, delete buttons. You've seen the use of the add button. The delete button simply takes away the selected load item in the list, and the edit button reopens the dialog that was used to create it in the first place. So it allows you to make some to the selected load item in the list. So that's a look at everything from the general sub-tab of the loads tab all the way through the lateral uniform sub-tab. Many different ways to apply your loads to your shear walls. The last of the input tabs is the load combinations tab. And here on load combinations we can see that we have 2 sub-tabs. One for service combinations, which are the load combinations that will be used for ASD design of wood, if that's the design method that's chosen, as well as for determining the service level soil bearing pressure if you've chosen to design a footing. Design method that's been chosen, and they'll be obviously used for concrete design if footing design has been selected. So let's come back to the service level combinations. The load combinations tab is very familiar and standardized throughout structural engineering libraries. So we have first the change load combination set button and the selected load combination set indicated. So let's just come down and choose IBC 2009 as our load combination set. Now the program has populated both the service level combinations and the factored combinations with those that are in the IBC 2009 load combination set within the program. We can come in and we can choose to do a run of only certain types of load combinations, but one thing that's important to understand the wood shear wall module is that the special design provisions for wind and seismic only provide guidance on how to design the sheathing for wind and seismic conditions. So it's an assumption within the wood shear wall module that we're only looking at the design of sheathing and chords for load combinations that include wind and seismic. Now for the sheathing, that's not much of an issue because that's pretty much all we would look at the sheathing for in a shear wall type sense anyway. However, if it happens to be an exterior wall subject to wind loads, then it's important to understand that you might need to take a look at the design of that sheathing for the out-of-plane effects. And when it comes to the chords, hoped that the chords would be dictated, the design of the chords would be dictated by lateral load combinations that include lateral effects, but it's possible that there could be a gravity-only load combination that actually is more severe to the design of those chords as far as load-bearing studs. And so for the chords, they should also be evaluated just like the common load-bearing wall studs would have to be evaluated. So that's a limitation that needs to be understood. For the footing, we are looking at all the different load combinations that are selected to run. So you may just choose to keep everything that's selected so that you can get a full look at soil bearing pressures and you can get a full look at reinforced concrete design from those load combinations. But just keep in mind that the shear panels, the sheathing, and the core are only being evaluated for the load combinations that include either wind or seismic. Okay, let's move on to the category labeled CD, which is your load duration factor, and just note that you can click the CD button and indicate that yes, you want the program to set the value of CD according to the load case with the shortest duration, and then those are automatically populated for you with the appropriate value from the NDS. The factors are all presented for you here on the basis of the selected load combination set, but you can also use the padlock icon to unlock those and come in and edit any of those factors on an individual basis as you see fit. And those edits will only affect this one particular calculation. They won't go back in and tamper with the original load combination set that's safely saved within the program. On the right hand side we have a note that says what I just described, that only load combinations with non-zero wind or seismic factors are used for wall and sheathing design. Okay, so that just reiterates what I just covered. If we choose to use the additional factor on dead load due to seismic effects, then we can check that box and come in here and enter a value of some sort so that it knows what to use in that multiplication, and then we would see those additional effects indicated on the dead load portion of our load combinations. Notice also that we have the familiar buttons to indicate that we want to automatically reverse the effects of wind loads and seismic loads. You can choose those, but please choose them wisely, because sometimes the wind loads and seismic loads that you assign are safe to assume can be reversed by an algebraic negative, and sometimes they cannot safely be reversed in that way. So that's what the function of these buttons would do, is just to simply create both the positive and the negative forms of all load combinations that include wind and or seismic. So use those as you see fit. All of the same information that we've just covered applies with regard to the factored combinations tab, with the exception that if we had chosen for our for our wood design method to be LRFD, then here in this column we would see a lambda offering, and we would not have seen the CD, the load duration factor, because in wood design we either use CD or lambda, not both. Okay, so that is a thorough look at the options that are available to us here on the load combination in the wood shear wall module. And that wraps up the information that's required for the input as we've moved from left to right in the normal workflow progression through the tabs in the top portion of the screen. The next thing that we'll do is take a look at some of the information that's available for us in the bottom half of the screen, which is results. Moving down to the bottom half of the screen to review the available results, notice that we have a shear panel design tab, and it offers 3 sub-tabs. Starting with the summary tab, we can review on a panel by panel basis, and notice the nomenclature here. P indicates panel, L indicates level, so we have panels at level 1, 2, and 3. And then within each level we start numbering panels 1, 2, 3, and so on. So we have 2 panels in level 1, for example. Here's an indication of the level as well. And then in the maximum shear category we have the number of the number of kips of load, shear load, that are assigned to each of these panels, and the load combination that produces that controlling maximum shear. Then we move into the number of sides of the individual panel that are sheathed. So here we can see that all of our panels have 2 sides of sheathing. The shear summary and attachment category shows us the actual shear in units of pounds per foot, the allowable shear in pounds per linear foot, the design status, whether it's okay or no good, and then a comment about the attachment. So if we had played around with some stronger sheathing, or if I had assigned slightly lower loads so that we had everything working okay, we would be able to see that we would have fastener patterns indicated for us. And remember that way back at the point where we specified sheathing, we've also specified the fastener and the minimum fastener penetration. So all the information is now provided for us. We know what fastener, and here we know what spacing to use. So notice that the shear accumulates from the top down. At level 3, which is the topmost panel, we can use fasteners at 6 inches on center at the edges and in the field. When we get down to level 2, we need fastener spacing a little bit. And then my 2 panels at the bottom partially hurt by the fact that I've added a penetration and also accumulating more shear, so their capacity is just exceeded at this point. The next thing that we'll do is move over to the height and width ratio category. Notice that we're reporting the actual height to width ratio for the indicated panel, the allowable height to width ratio for side 1, which is referred to as the main sheathing side, and the allowable height to width ratio for side 2, which is the second side sheathing. So for instance, what we can see here is that we have a height to width ratio of 1.2. So compared to the allowable of 3.5, which is sheathed with wood structural panels, we're fine. We're within that allowable. And compared to even the allowable on side 2, which is sheathed with gypsum wallboard, we're still less than the allowable height to width ratio. So the aspect ratios are okay. We do note that it has to be blocked. The wall framing does have to be blocked for the height to width ratio that has occurred, but there is no reason why we couldn't use that height to width ratio. So some valuable design information here, and what we'll also see is that if we define a wall that requires an adjustment to the shear capacity, the unit shear capacity of the selected framing on the basis of its height to width ratio, the program will actually take care of that for us, and we'll see that when we move over to panel by ID. Here we'll make a little bit more these capacity factors. So that's a segue into the detail by panel ID subtab. If I collapse the information that we have here, we can see the same form shaping up, that we have information about panels at levels 1, 2, and 3, and for each individual panel within each level. But now we have it on a load combination by load combination basis, and remember, this having to do with shear panel design, we'll only see load combinations indicated here that have either wind or seismic as part of their definition. The panel data category lists what story the selected panel is in. It indicates the value from the left edge of the wall to the left edge of the panel, which for this particular panel happens to be 0, but if I expand this a little bit, we can see that panel 2 starts at the 4th dimension, and it happens to be 11 feet wide. The category called bottom is the dimension from the bottom of the wall to the bottom of the panel. So if we wanted to see a meaningful non-zero value there, we could come up to the panel at level 2, and here we can see that all panels at level 2 start 12 feet above the bottom of the wall. And then we see the height of the panel indicated. So story 2 is defined as being 11 feet tall, and we report that the height to width ratio for the panel. If I move back down to level 1, we'll see a value here that's meaningful. It's called trib width. And what this does is it determines what fraction of the shear in the given story is tributary to this panel. It may be even more meaningful to take a look at the tributary percent, and here you can see that 0.6% of the shear in level 1 goes to this panel, and if I collapse this, we should see in the other panel something just over 50% going to panel number 2. So that again is the panel length divided by the total effective panel length at the given level. Then for each load combination, we see the shear that results in. We have the actual panel width, and then we have a shear, which is the number of kips divided by the panel length. So we have a force reported in units of pounds per linear foot. The next category is called capacity factors. The first column indicates an adjustment factor depending upon the selected design method. So if we had RFD method, we would see a phi value, and that would be 0.8. Since we've selected the ASD method, what we see here is the reciprocal of the factor of safety. In other words, we're multiplying by 0.5 where the code tells us to divide by 2, so mathematically the same thing here. This is a design method adjustment factor. The next column reports a capacity adjustment factor if necessary due to the aspect ratio of the sheathing on side 1. In this case, it happens to not require any adjustment. The next column is any necessary adjustment due to the aspect ratio of the sheathing on the second side of this panel. Again, in this example, the adjustment factor of 1.0 means that we don't need to make any adjustments. And then the last capacity adjustment factor is one that's specified for the specific gravity of the framing. So remember, way back on the General tab, we've selected the framing and chord material, which included a specific gravity. And then here, in accordance with the special design provisions for wind and seismic, we're making any necessary adjustment to the nominal shear capacities for the selected sheathing based on the specific gravity of the framing that the fasteners are penetrating into. The next category is called adjusted allowable shear. So what this does is it takes the nominal shear values for the various fastener spacings for the selected sheathing on side 1 and side 2. It factors them appropriately for the design method, the aspect ratio as necessary, and the specific gravity as necessary, and then it combines logic that's specified in the special design provisions for wind and seismic as dictated for the selected load combination. What that means is that special design provisions indicate that we do certain things for determining the allowable strength when resisting wind load combinations, and we have to do some potentially different things when we resist shears due to load combinations that incorporate seismic effects. So embedded behind these values is both calculation and logic to determine how to treat the values of resistance from side 1, the main side, and potentially a side 2 for the particular load combination that's referenced over here at the left. A lot of information going on behind these values, a lot of work and a lot of logic taking place to report the controlling value that you need to compare your applied unit shear to in order to come up with a required fastener spacing. Okay, then moving over, we have the panel moment indicated here in units of foot kips, and finally, for convenience, we identify the chords at the left and the right end of each panel. So the left hand chord for the panel L1 number 2 is called chord L1 number 2, and the right hand chord for the panel L1 number 2 is referred to as chord L1 WR, which stands for wall right. And that's because panel 2 is on the right hand side at this level, and so it always uses a wall left or a wall right designator for its chord, just to frame of reference for you and to help you to understand where you are in the physical space of the wall itself. So that is the panel, the detail by panel ID sub-tab of the shear panel design tab. The last one is called detail by load combination. So here, on a load combination by load combination basis, we report information for each of the panels, which includes that tributary length, which again is really another way of expressing the tributary percentage of the shear that goes to the named panel. And then we use that percentage and the total shear at the level to report a shear force for that level. So the detail by load combination sub-tab really is just providing us with shear forces and tributary percentages for each of the panels. Here on the right hand side is the nomenclature that we're using to define panels, levels, chords, and so on and so forth. The next major results tab is called chord design, and the first sub-tab that we have is called chord data. The chord data sub-tab presents us with information for each and every chord in the model. It provides us with which level the chord is at, the distance from the left-hand edge of the overall wall to the named chord. And then we start in with the chord design category, where we can see an indication of the force in the chord, the load combination that produced that force, and a very important piece of design information here is the number of members required. Remember, all the way back to the chords tab, what we entered was the size, the 2x6 size. But the program is actually determining how many 2x6s are required at each location. So if we envision this as an upside down building, we can see that at level 3 and at level 2 we only require one 2x6, but when we get down to level 1 we actually need to double them so that we have two 2x6s at each and every chord location in this wall. The ratio is indicated, so 20.6% utilization of that single 2x6 at level 3, moving to something more like about 60% utilization of the double 2x6 in the bottommost story. The governs column indicates that tension happens to the particular design, and the status column indicates that the designs are actually all okay. We were able to find, by doubling or multiple built-up members, we were able to find a design that was acceptable for each of the locations. The chord compression stress category reports the maximum compressive force that's experienced by the named stud, the load combination that's responsible for generating that compressive force, the maximum compressive stress that's experienced by the named stud, and the maximum allowable compressive stress. And then the chord tension stress category reports all the same information, but for the tensile perspective. So the maximum tensile force is reported, the load combination that's responsible for it, the maximum applied tensile stress on the member, and the allowable tensile stress. Next, we can move over to the chord forces by chord ID subtab, and here we can see information on a chord member by chord member basis. For each chord, we can read detailed information on a load combination by load combination basis. So we can see what story the chord exists in and what the chord ID is. And then we start in with the axial category. Now let's just scan down through and see if we can find one that's of interest here. So at level 2, the chord that's at the left edge of the wall, for a particular load combination here, we can see that we do have an applied load. This would be due to either applied uniformly distributed loads or concentrated loads or loads from above. But we have a 0.5 kip load on this particular chord member. The next column over reports the panel overturning force. So there is potentially some overturning moment in this panel which can be coupled out by the distance between its chords and resolved into a compressive or tensile force, and that's what this magnitude is. So since wind and seismic can come from the left or from the right, what we need to do is we need to take this number plus this number, and that generates the maximum compressive force over here. And we also need to consider the opposite direction of overturning moment. So this value minus the overturning force, and that produces this maximum tensile force that could be experienced by the chord. Next, we move to chord location, and what we're doing here is we're locating the chord with respect to the left of the overall wall. So if I was to take a look at a detail of a chord that's at the right hand end of the wall, we can see that we have a 25-foot dimension there because I've defined the wall as being 25 feet long. And then if I was to go up to something other than level 1, like if I come to level 2 wall right, we can see that it's also at 25 feet, but now we start to pick up some elevation as well. The bottom of this chord is at the 12-foot elevation, the top of this chord is at the 23-foot elevation. So that's the information presented on the chord forces by chord ID subtab. The next results tab is called footing and stability, and I would point out that this will only be visible if you've chosen the option to design a footing up here on the footing tab itself. At the left side of the footing and at the right hand side of the footing in units of PSF, along with their respective governing load combinations, the load combinations that produced these pressures. Now these are factored soil pressures, so not something that you'd want to use necessarily to compare to an allowable in a geotechnical report, but instead they're reported for reference because these are the values that are being used to drive the force that ultimately is creating the design loads for reinforced concrete design. Next we have footing one-way shear check, where we report the shear stress at the left end of the footing and at the right end of the footing. In this case, I believe that I've left my footing projections very short, and based on the projection length and the footing thickness, we're at that aspect ratio where there really is no shear stress. So that's why we're seeing 0 values here. But in longer projections of more substance, we would actually see shear stresses being reported, and then we see a phi-VN value that we can compare those to. The next category down reports the bending moment design information. It's presented at both the left end of the wall and the right end of the wall, so we can see a factored applied moment at both ends, an RU value that's reported, an area of steel or a percentage of steel, in this case it's an area of steel that's required, and then a recommendation for reinforcing bar patterns. So in this case 3 number 4s would do the trick, 2 number 5s or 6s, or even a single number 7 bar if you were so inclined. If we upper right hand side, we now come to the maximum unfactored soil pressures. So here we're getting into a service level soil pressure that's meaningful to compare to a geotechnical report, and we can see results reported at both the left end of the footing and at the right end of the footing, each with its governing load combination, the load combo that's responsible for producing this soil bearing pressure. And then we have the overturning stability calculations, where we report the moment about the left end of the footing and indicate the overturning moment, the resisting moment, and the ratio resulting, all from this governing load combination, and then the same information at the right end of the footing. So here we can take a look at quickly in bold the stability ratios against overturning about both the right end of the footing. The last piece of on-screen information that we'll take a look at here is the sketch tab, and here we see an overall view of the wall with familiar options to turn on and turn off, dimensions, loads, chord labels and graphics, shear panel labels and graphics, and even to turn off the opening labels and graphics. In conclusion, the last thing we want to mention is that as with all calculations in structural engineering library, you have the ability to print a nicely formatted report. So print to your printer and visit the print properties icon so that you can refine the details of what will be included in your print. We certainly hope that the video has been useful, and we hope that the module itself is useful, and as always we welcome any comments that you may have on either the video or the module itself and the functionality that's provided within. happy to receive those comments, and we'll do our best to try to respond to anything we can that would improve the module or add functionality for you. So thank you very much for watching here. Take care, have a great day, and enjoy the new module.